Good afternoon, everyone. Let's start. Right, so in the last class, we were discussing some of the basics of probability and in particular, some applications of
Sir,
the concentration inequalities that were introduced earlier.
sir, we're not
Right,
able
so
to
we
hear
used
you.
the Chebyshev inequality to get an idea of the geometry of high-dimensional Gaussian random variables. In particular, we saw that as if for very, very high dimensions, that is n much larger than 1, most of the probability of an n-dimensional IID Gaussian vector is concentrated in a thin shell, right? And so it's in between two balls. One, the outer ball being of radius n sigma square, so square root of n sigma square into 1 plus epsilon, and the inner ball having radius square root of n sigma square into 1 minus epsilon. Okay, so this is a peculiarity of high dimensions, and it's good to keep, although this is kind of counterintuitive, it is good to keep this in mind because we'll be using this further on. So, but probably what is more important is to uh, remember the fact that if you look at a high dimensional Gaussian random variable, Gaussian random vector, then most of the probability lies at least within a ball of radius square root n sigma square into 1 plus epsilon. Right? So the probability that the Gaussian random vector lies outside this ball is actually very small. It's actually exponentially small. But okay, but the geometry aside, so this is an application of these inequalities, and we'll be using some of these inequalities as we go on later at a later point in this course. Okay, so any questions regarding the topic that was discussed last class? Okay, so one minor point. So when I did the calculations involving the Chebyshev inequality in the last class, I was missing a square over here. So if you apply the Chebyshev inequality on this particular quantity, then it's not sigma square epsilon in the denominator, it is sigma square epsilon the whole squared in the denominator. And finally, once you simplify, you will get that this probability, the probability that it is not in the shell, is upper bounded by 2 by n epsilon square sigma, which anyway tends to 0 as n tends to infinity. Okay. All right. So if there are no further questions, the only other topic that was in the video was sequences of random variables. So you know what an IID sequence of random variable is, and hopefully now you're also familiar with the concept of a Markov chain. So this is the simplest uh, model for a sequence of random variables where you have a certain amount of memory. So IID sequences are kind of memoryless in the sense that every random variable in the sequence is independent of everything else. Right? But for Markov chains, conditioned on the first or on the previous random variable, so conditioned on xi minus 1, the random variable xi is independent of everything else in the past if it's a first order Markov chain. Right? So similarly for kth order Markov chains, every xi in the sequence depends only on xi minus 1 up to xi minus k. So conditioned on the k previous random variables, it is independent of everything else. And very shortly, we'll see why this is important, why such a model makes sense, and how these are applied to the problem of compression. Okay, but all of these can be generalized. So note that an IID sequence is a special case of a Markov chain. It is a zeroth order Markov chain. Uh, but you can also generalize Markov chains, uh, not exactly generalize, but But many of the results can be that we'll see in this course can be generalized to what are called stationary random sequences, and this is essentially what is sometimes called strict sense stationary sequences. So strict sense stationary sequences, you take any subset of locations in the sequence, and then the probability the joint PMF or the joint PDF of that particular set of random variables is the same as if you had shifted. So you have x1, x2 up to so on. So the joint PDF of x1, x2 is the same as the joint PDF of x2, x3, and it is the same as the joint PDF of whatever xi plus 1. And this holds not just for pairs, but for triples or any set of random variables. Okay, so that is what is called a stationary random sequence, and many of the results that we have can be generalized to stationary random sequences. So every IID sequence is stationary, but not every Markov chain is stationary. So wherever we talk about Markov chains, we generally assume that these Markov chains have a stationary distribution. So for most part of this course, I will talk only about IID sequences, but then it's good to know what a Markov chain is, and the fact that a lot of this can be generalized to stationary Markov chains and more general stationary random processes. Okay, any questions? All right, so in that case, we'll start with the first problem that we're interested in, and that is source coding, or in other words, data compression. So let me just pull up those slides. Okay. So one of the first problems that was studied in information theory was the problem of data compression. In fact, the information theory that we're going to study in this course essentially was born out of a paper by Claude Shannon in 1948. It was called A Mathematical Theory of Communication. So the title of the paper was A Mathematical Theory of Communication. It was by Claude Shannon. And it was this landmark paper which sort of introduced the area of information theory. In this paper, he talked about two problems. One was source coding or data compression, and the other problem was how to communicate reliably over a noisy channel. Now, this paper did not give any algorithms. He didn't say how do you compress data. He didn't give us any specific algorithm for compressing data or even for communicating across a noisy channel. And that was the beauty of it. So even without giving a specific algorithm, he still showed that if you model these problems in a certain way and quite a natural way, then there are these fundamental limits. There are certain things that you can do, and there are certain things you cannot do, and there's a very sharp threshold between what you can do and what you can't do, and it was only after this paper, several decades after this paper, that we actually designed efficient algorithms in order to get to those fundamental limits. So we'll see what those fundamental limits are. And in a sense, information theory is all about discovering these fundamental limits about these problems. So the first problem that we look at is data compression, and this is sort of a block diagram representation of the data compression problem. So we have a file, a raw file. It could be a text file, it could be an image, it could be a video, it could be an audio file, doesn't matter. So it is a raw file, and this is, then we'll also sometimes call this a source or a source sequence. So we'll assume that this file can be represented in the form of a sequence of n symbols. So this is in the form x1, x2, up to xn. So n is sort of the size of the file or the length of the sequence. We don't care what the individual symbols of this sequence are, in the sense that you could treat, for example, if you're talking about text files, you could treat a text file as a sequence of characters, or as a sequence of words, or as a sequence of sentences, right? So you could say that the text file has n sentences, or while modeling, you can say that it has a sequence of n words. But as it will turn out, irrespective of what the of how you are modeling this particular source, thus the algorithms may change, but the end result of what we are about to study is not going to. So anyway, so we have a raw file, or the source sequence. Our goal is to somehow convert this into a compressed file or a code word. So we have a raw file of size n, which contains n symbols, and we want to convert this into a compressed file which has k bits. So whatever 0 1 0 0 1 1 0 1 1 1, whatever, it's a compressed file. So it belongs to this particular set 0 comma 1 to the k. So this is the set of all possible binary sequences of length k. So we have the raw file, and we want to convert this into a compressed file, right? So in order to save space. Now that's not enough, because after all, we want to get back the raw file from the compressed file. All right. So in order to go from the raw file to the compressed file, we use what is called a compressor, or more generic term for this is what we call an encoder. So a compressor or an encoder takes the raw file as input and outputs and gives the compressed file as output. Now, in order to get back the raw file or some version of the raw file, we use what is called a decoder or a decompressor. So a decoder or decompressor is going to take as input the compressed file, which is a sequence of k bits, and it is going to output the decompressed file, or sometimes it is called the reconstruction, or it's called the estimated sequence. So there are different terms used for the same thing, but that doesn't matter. So whenever I say decompressed file, or the reconstructed sequence, or the reconstruction, or the estimate, I'm referring to the output of the decompressor. And whenever I'm saying compressed file or code word, I'm referring to the output of the encoder or the output of the compressor. Okay. So this is the simple block diagram of any compressor, or of any compression problem. Right. So the first thing to observe is that, suppose, let's assume that the raw file is a sequence of n bits, right? And the compressed file has to be a sequence of k bits. Now, if I demand that k always has to be less than or equal to n, then it is impossible to reconstruct the original file always, right? You might be able to reconstruct some of the raw files, but not every raw file can be reconstructed. So if k is less than n, and we're dealing with only binary sequences, then not every raw file can be reconstructed back at the decompressor. Do you agree?
Sir? Hello? Sir,
right? So
can
why
you
is that the case? So why can't you reconstruct every file? What happens if k is strictly less than n?
so 1 minute. So n x1 x2 up to xn are bits.
Yeah, we're assuming that x1, x2 up to xn are bits. So I have an n length sequence, binary sequence, which is my source sequence or raw file, and I want to compress it into k bits, where k is strictly less than n. Then I cannot always get back the raw file. Remember that the encoder or the compressor and the decoder or decompressor, they're fixed beforehand. Okay, and for every raw file I give as input, it is the compressor is always going to output a sequence of k bits. The decompressor is always going to output some sequence of n bits. But okay, so but the output of the decompressor may or may not be equal to the raw file. But the question is, can I always design encoder and decoder such that the decompressed file is exactly the same as the raw file? If k is less than n, it is not possible. Why?
So when k is less than n, some information in the raw file is discarded. Information in the sense like uh, maybe uh, certain redundancies or something.
I'm
When
sorry,
you
your voice
reconstruct.
is very, very low. Can you maybe increase the mic volume?
Hello. So now,
Slightly better.
when when k is less than n,
Mhm.
the thing is like we will be discarding some bits from the
Okay.
source, so so that information is lost, which we can't reconstruct exactly after the in the decoder. So because of that.
Okay, so that intuition is correct. So another way to think about it is the following.
So when the sequence of the raw file is like all of them are different, then it may have a problem.
Sorry, if the raw file, can you repeat?
So the sequence that we have, the source sequence, the n symbols that we are talking about, if all of them are different and they are independent in nature, and there's no redundancy between the symbols. That means if we take x1, xi is not equal to xj for all I comma j. In that
Okay.
case, if we do the compression, the k-bit compression part of it, if it is less
Uh-huh.
than n, that means we are ignoring some symbols in that case.
Okay.
So that way it may be a problem if it's not like having any redundancies.
Uh, okay. Fine. So another way to think about it is the following. So we have these algorithms, the encoder and the decoder, right? Now let us list all possible raw files that can be given as input to the encoder. Right? So there are all zeros, 0, 0, 0, 0, 0, 0, 0, 1, and so on, all the way up to 1, 1, 1, 1, 1, 1, 1. Okay, so how many sequences are there? How many possible input files of length n can there be?
2 to the power n.
2 to the power n. Very good. Okay. So let's assume that I give each of these sequences as input to the encoder, okay, or the compressor. Okay, so for each of these, I have the output, which is going to be some sequence of k bits. I don't care what it is. I'm fixing the encoder and the decoder, but I don't care how it is spitting out these sequences of length k. So the input is always a sequence of length n. The output is always a sequence of length k. Right, so something, I don't care how it is, but whatever, the encoder has there is some rule by which the sequence of n bits is converted to a sequence of k bits. So, and then I have the decoder, which for every sequence of k bits at the output, it is going to output a sequence of n bits an n-bit sequence, right? So now, if since the number of possible inputs to this encoder, so think about the encoder and decoder as functions, right? So if there are 2 to the n possible inputs to the encoder, and the output so how many output sequences are there? There are only 2 to the k distinct sequences. There are only 2 to the k distinct sequences of length k. So which must mean that since the number of possible outputs is only 2 to the k, the number of possible inputs is 2 to the n, the encoder must map 2 different input sequences to the same output sequence, right? So 2 distinct input sequences or 2 distinct raw files must be mapped to the same compressed sequence or code word, right? But now once it has been compressed, it is impossible to say whether sequence 1 occurred or sequence 2 occurred, because given the compressed sequence, it is impossible to get back to know whether the first sequence occurred or the second sequence occurred, right? And therefore on one of those 2 sequences, at least on one of those 2 sequences, the decoder is going to make an error, right? So obviously it is not possible to obtain compression of every possible input sequence, right? That's impossible. So the question is, now how do we obtain compression, and how do we even model the compression problem, right? Are we looking at arbitrary input files, or do the input files have some structure to them? And in fact, we'll only look at those input files which have some structure. But of course, this can be generalized to more arbitrary sequences. But for now, we'll assume that the input files have some kind of structure. Any questions? Okay. So in fact, the model that we will use is the following. So we will assume that the input is not an arbitrary sequence, but it's a random sequence. So the file or the source is going to be a random sequence or a random source, and it follows some probability distribution. Let's say that the distribution for xn is some pxn. We assume that each symbol, this consists of n symbols, and each xi comes from some set, let me call it script x, which is called the source alphabet. Right? So for example, if I treat the input as a sequence of ASCII characters, then the source alphabet is the set of all possible ASCII characters. If I'm only looking at English text files, then maybe the source alphabet is the English alphabet along with punctuation marks and spaces, right? Or generally, if it's maybe an image, then maybe it is a sequence of RGB values, or if it is an audio file, then maybe it's a sequence of amplitudes, right? So, but whatever it is some sequence of length n. It comes from some source alphabet, and we assume that this is a random sequence that follows some probability distribution pxn. Okay, so that will be the basis of, or that will be our fundamental assumption when solving the data compression problem. Okay, because after all, we need to make some assumption on the source, without which we can't design a compressor. So the assumption will be that the source sequence is random, and the source sequence follows some probability distribution pxn. Okay, so this is the source distribution. is Pxn. Okay, and in fact, we'll make an even more simplifying assumption to begin. For now, we will assume that the source sequence is memoryless. So in other words, we'll assume that.
Sir,
Yes, I think there's something else. Okay. Yeah, sorry, not sure what happened, but
sir,
yes.
for the encoder and decoder, you put an arrow and said n comma pxn. So pxn is the probability distribution. You said n is what?
So n is the length of the file, the source.
For encoder, input is n bit file, but for
Correct.
decoder, it's a k bit input. No, sir.
Correct. But so I'll come to that in just a moment. But we'll assume that both the encoder and the decoder know what n is, right? So they know what the length of the decompressed file or the length of the raw file is equal to. And in addition, we will also assume that the source distribution is known to both the encoder and the decoder.
Okay, sir.
So so Pxn is what we call the source distribution, and we'll assume that the sequence is memoryless. So we assume that Xn is IID according to some known distribution Px. And so our assumptions are as follows. So we assume that Xn is random. Okay, just to make our life simple. And at least for this course, we will assume that we will in fact assume that Xn is IID according to some distribution Px. And the third assumption that we will make is that Px is known a priori to the encoder and the decoder. We won't bother about how it is known, but we will assume that this is known. Note that this is a very standard assumption, and this is used to design good compressors. But of course, these assumptions are not terribly good, right? Because in general, if someone gives you, say, a text file, of course, the text file is not going to look like an IID sequence, and of course, you don't know what the distribution is when compressing or decompressing, right? So these are not assumptions that are made in practice, but at least to understand what the fundamental limits are, we will make these assumptions that Xn is IID and it is known to both the encoder and the decoder. And the reason we make these assumptions, we generally make these assumptions, is because it's easier to describe the solution to the problem, but of course it's also pretty simple to extend it to the case when the sequence is not IID and when the input is not known to the encoder and decoder. Okay, and in fact, I'll give a solution, a more general solution, which holds even without the second assumption, but the third assumption has to always be valid. So we will always assume that the joint distribution, whatever it is known to both the encoder and the decoder. It is available for free, but we may or may not make this assumption that Xn is IID according to some distribution Px. It could have memory. It could be an arbitrary sequence. It could be an arbitrary joint distribution. Okay. Any questions so far? So both the encoder and the decoder, they know what the joint distribution is. They know what the length of the raw file is. Okay, and the goal is to somehow design these encoders and decoders such that you can reconstruct XN, whatever that means. I'll make this more precise in a minute, but yeah.
Sir, where are we talking about the joint distribution? It's the marginal distribution, right, at the moment?
Sorry, can you please repeat?
You said like the source and that means the encoder and the decoder is aware of the distribution.
Yes.
So we are only talking about the marginal distribution here, right? Not the
No,
joint
so
distribution.
assuming that you know the distribution of the entire sequence XN, not just the marginals PXIs. Right?
Okay.
So for example, if the sequence is IID, then it is sufficient to just know the marginal distribution PX1 or PX2. But then if it is a Markov source, then I'll assume that we know not just PX1 but also PX2 given X1.
Okay. Okay.
Right. So in general, if
that
it
will be
is
a conditional distribution.
Sorry.
That will be a conditional distribution we'll be talking about.
Yeah, so whatever so basically if you know the conditional distribution and the marginals, you know the joint distribution, right?
Okay, sir. Okay.
So
got it.
So in general, so firstly, I will not make any assumptions about PXN. It could be Markov, it could be stationary, it could be IID, doesn't matter. But then later on, I'll make the assumption that the sequence is IID. Okay. So these okay. Right now, good. Okay. So we have K and we have N. So the N symbols are converted to a sequence of K bits. So here's a definition. So we define the rate of any compressor to be this ratio K over N. Okay, so it is the size, or in some sense, it's a measure of the ratio of the size of the compressed file to the size of the raw file. And our goal is to design these compressors and decompressors such that the rate is as small as possible. Okay, I'll make things a little more precise because the way I have posed the problem right now, it's not complete. There is some missing information. Okay, and that is the following. So depending on what the reconstruction or what the decompressed file has to satisfy with respect to the input file or the raw file, we can categorize the problem of compression into two broad classes. One is lossless compression and the other is lossy compression. Now, in certain applications, such as text compression, we want to make sure that the output or the decompressed file is exactly the same as the raw file, right? It cannot be any different. But then in certain applications, such as image and video, it is okay if the reconstructed file, if the decompressed file is slightly different from the original raw file. So for example, if you take a DSLR and then the DSLR is going to give you some image, right? So some which is generally in some format, say a raw format, and this is generally converted to JPEG or PNG or whatever your favorite format is. And the process you go from the raw file to this JPEG or whatever format is using some kind of a lossy compression method. So the output is not exactly the same as the input. There is some loss of quality, but then it's still good enough. So another simple example is let's say that you have a photograph, some picture, some image file in your cell phone, and you share that image on, let's say, WhatsApp, right? If you notice the image which is shared on WhatsApp, the quality is lower than the original image which is there in your phone, right? So there is some loss in quality, but then it is still roughly the same image, right? So if you don't zoom in, if you don't view it at high resolution, it looks the same as the original image. So that is an example of lossy compression. when we're talking about text, we can't lose a single bit of information, right? It has to be the output, the decompressed file has to be exactly the same as the compressed file. If I give it a PDF as input, the output PDF should be exactly the same thing. If I use zip, then the output, when I compress, say, a text file using zip, and then I decompress that zip file, I'll get a copy of the raw file. Right? There cannot be any difference. And in such cases, we want a lossless compression algorithm. All right. So a lossless compression algorithm is when, okay, so let me start with a lossy compression algorithm. So a lossy compression algorithm is where the decompressed file need not be equal to the original raw file. So we allow some loss in quality or some distortion is permitted. Okay, but in a lossless compression algorithm, we want xn hat to be equal to xn, depending on with some additional qualifier. So even lossless compression algorithms, or generally compression, so based on lossless versus lossy, based on loss, you can categorize a compression algorithm into a lossless compression algorithm and a lossy compression algorithm. There's another way of categorizing compression algorithm, and that is fixed length compression versus variable length compression. So fixed length compression algorithm is one where k, the size of the compressed file, is fixed, and this depends only on n and possibly the input distribution, right? So as long as the distribution is fixed and the length of the sequence is fixed, the value of k, the size of the compressed file, is fixed. It doesn't depend on anything else. In particular, if I randomly choose an xn according to pxn and pass it through the compressor, I'm going to get a sequence of length k. If I draw another sequence randomly and feed it to the compressor, again the length is going to be the same. It is not going to change. Whereas in variable length compression, even for the same n and px, I allow k to vary. Can vary even if n and pxn are fixed. So in particular, if I give one particular file as input, same size, sequence of length n, maybe I feed a 1 MB file as input. For that particular file, the compressor may output a file of length 100 KB. Now for a different 1 MB file, the output may not be a 100 KB file. Maybe it is 102 KB, right? And so on. And for example, if you look at zip or rar or most commonly used compression algorithms, these are all variable length compressors. For the same input, for inputs of the same size and the same statistics, the output could be slightly different, right? So for example, if I give a sequence of let us say bits to zip, then the output, the compressed file, the size of the compressed file could vary. Okay, and that is what is called variable length compression. In contrast, fixed length compression, if I give a 1 MB file as input, no matter which 1 MB file I give as input, the output is always going to be, let's say, 100 KB. Okay, it is not going to change. All right. Is this clear? Are there any questions?
So,
Sir,
Go ahead.
sir, just in case we have a single file that you said about 1 MB is converted to 100 KB and the other case is 102 KBs.
Correct.
If a same file is there, sir, and we are going to compress it at multiple time, let's say with zip it at one time and again zip it to the other time, so
Okay.
this will be the case, or is it like
No, that's a good question. So if I give the same file, no matter how many times I give the file as input to the particular compressor, the output always has to be the same. That is going to remain fixed. So if I take a 1 MB text file, maybe this is I don't know, it's a copy of Harry Potter. Potter part 1. I feed it as input to zip, and I'm going to get a file of size 100 kilobytes. Now, if I try to compress the same file tomorrow, I'm still going to get a file of size 100 kilobytes, even if I use a variable length compressor. Okay, but then now instead of Harry Potter 1, I give maybe Harry Potter 2, which is a different text file. Maybe that is also of size 1 MB. The fixed length compressor is always going to output a file of size 100 kilobytes, whereas the variable length compressor could output a file of size 102 kilobytes. But then if I give the same, no matter how many times I give the same file as input to the compressor, it's always going to give the same output. Not just the size, but also the compressed file is going to remain the same, even if it is a variable length compressor. Is that clear? Okay, good. Any other questions? Okay, good. So now we've seen that there are two different types of compression: fixed length and variable length. Now, so therefore, what variable length compressors do is that for certain files, let's assume that we have fixed n, we have fixed pxn. Now, once these are fixed, k of course can depend on the input sequence. So k can depend on xn. So for certain files, you're going to get very small compressed files. For certain files, the compressed file size is going to be very large. Right? So that is what a variable length compressor does. So how do we measure the performance of a variable length compressor? Because now the rate is not fixed, right? So the variable length compressor, the performance of a variable length compressor is measured using what is called the expected length. Right? So now k can depend on xn, and the expected length is basically the expectation of k of xn, right? And the average rate. So we measure the performance using the average rate, which is the expectation of k of xn divided by n. So for example, to give a sense of what a variable length compressor might do, let us take a very simple example. Let's assume that there are only, let's say, 4 sequences in the universe. The only goal now is, so we'll assume that n is equal to 2, and we're only interested in in compressing this binary, in compressing these 4 possible sequences. Okay, or another way to look at it is that, okay, I have 4 possible sequences. All right. Now, if I didn't compress it, then I would require 2 bits. Right. So n equal to 2. Now let us assume that some sequences occur very frequently and some sequences occur less frequently. Let us assume that 0, 0 occurs with probability, let us say 0.5, 0, 1 occurs with probability 0.25, 1, 0 occurs with probability 0.125, and 1, 1 occurs with probability 0.125. Right? So this is the probability of occurrence of xn. Right? Now I give, let us say that what my compressor does is the following. So if the input is 0, 0, it outputs 0. If the input is 0, 1, it outputs, let us say, 1. If the input is 1, 0, then it outputs 0, 0. If the input is 1, 1, the output is let us say 0, 1. Okay, this is a compressor, whatever, right? So here, as you can see, K varies with N. K varies with the input sequence, right? So this file is compressed to 0. This file or this sequence is compressed to just bit 1. 1, 0 is compressed to 0, 0, and 1, 1 is compressed to 0, 1. Right? So this is my CK. This is my compressed sequence. Okay. So the decompressor, of course, if the decompressor just sees bit 0, 1 bit 0, then it knows that it has to output 0, 0. If it sees bit 1, it knows that it has to output 0, 1. 0, 0, it knows that it has to output 1, 0. And if it sees 0, 1, it knows that it has to output 1, 1. Okay, this is some variable length compressor. Okay. So now what is the expected length of this compressor? So firstly, the compressor and decompressor are clear? Are there any questions?
Sir,
Yes.
we have considered some kind of a mapping here at the compressor side.
Correct.
Like just I'm asking, like in case like here we have 0 1 0 0 0 1 in the compressor's side. So when the decompressor is reading it, how would it read, like 1 bit and 2 bits? It won't be able to find out now, sir. Like initially I get 0 and 1. How would it know if it has to take 0 0 0 1 or just 1 1?
I'm not sure I get. So is the problem that the decompressor doesn't know when to stop reading? Is that the question?
Like, sir, the first thing, in the compressor side, we have mapped 0 0 to 0
Correct.
and 0 1 to 1.
Correct.
So now when the decompressor reads 0 1, it should
Okay.
map 0 to 0 0 and 1 to 0 1.
Okay.
How?
So the question is, why doesn't the decompressor, so if it sees 0, 1 as its input, why doesn't it output 0 0 0 1 as the input? Is that the question?
Yeah, that is one thing.
Correct. So here again, we're making the simplifying assumption that n is known to us, right? So here we know that n is equal to 2, and we know pxn, and that is why the decompressor knows that if it sees 0 1, it has to output a sequence of length 2, not a sequence of length 4, because we're assuming that the decompressor knows n, right?
So in that case, only one decompressor can output only 1 0 and 1 1.
Correct.
Okay,
So
sir.
we're assuming that we have only one sequence to compress. The length of the sequence is known. The distribution of the sequence is known. Now, I agree with you that practical compressors have to do a lot more, because of course you don't know what the length of the input sequence is. You don't know what the distribution is. But these are simplifying assumptions that we will make at the moment.
Okay, sir. So this is the reason for compressing to a different size, like in that variable
Correct.
length compression for the same 1 MB, because two 1 MB files can have different bits. I mean, different information.
Yes, exactly. So two different 1 MB files can be compressed to sequences of two different lengths.
Okay, sir.
Right?
Thank you.
So in fact, when we if you take the source coding course, which will be offered in segments 3 and 4, we will investigate these variable length compressors in more detail. In fact, we'll see that the compressor that I have given over here is not a very good compressor, because of precisely the reason you pointed out, that if the decompressor says 0 1 as the input, and in case it does not know what the length of the input sequence is, then it doesn't know whether it has to output 1 1 or it has to output 0 0 0 1. But for now we're assuming that n is known and pxn is known, and that is what simplifies things. Any other questions? Okay, so what is the expected length of this particular compressor, or the expected compressed length?
1.75.
Well,
1.75 bits.
1.75. Okay, very good. So it is just 0.5 into 1 plus 0.25 into 1 plus 0.125 into 2 plus 0.125 into 2, which is 1 plus 0.5 plus, sorry, this is 0.5, 0.5 plus 0.25 plus 0.125 into 2 is 0.25, 0.25 into 2 is 0.25, so it is 0.5, so it is 1.25. Right? Okay, so this is the expected length of this variable length compression scheme. Now let us assume that I used a fixed length compression scheme instead. Okay, so here if I have this variable length compression scheme, then I can always ensure that the output is exactly equal to the input. So in variable length compression, we will generally assume that we will demand that xn hat has to be exactly equal to xn all the time. Okay, but now if I have a fixed length compressor, let us say so I have the same problem, but now I don't want a variable length compressor, I want a fixed length compressor. And obviously if I want any level of compression, then I have to so I need to take k equal to 1, right? So okay, so let's say that I'll assume that this is mapped to bit 0, this is mapped to bit 1, this is mapped to bit 0, this is mapped to bit 1. This is one compressor, right? So in this case, the expected length is 1.25. The average rate is 1.25 divided by 2, right? So it's expected k of xn divided by n, which is strictly less than 1. So the expected length is strictly less than 2 bits, which is much better than 2 bits, which is the length of the input sequence. If we didn't have any sort of compression, then we need 2 bits to represent the source. All right, so now I'll use a fixed length compressor where k is equal to 1 bit. Okay, but now the problem is that if I see the input, I can't get back every possible output sequence, right? Because all the decompressor sees is either bit 0 or bit 1. And now there is no way to say whether the actual file was 0 0 or it was 1 0 if the input was bit 0, and whether it was 0 1 or 1 1 if the input to the decompressor is bit 1. So let us assume that the decompressor does the following. So if it sees as input bit 0, so this is the encoder or the compressor. So the decoder, if the input is bit 0, it will output 0 0. If the input is bit 1, then it outputs 0 1. Okay, this is some decompressor, right? So we know that the rate is equal to half, which is 1 over 2. But now it is going to make some error, right? On some of the input files, it is going to make an error. It has to, because then there is no, because otherwise there is no way of reconstructing. There is no way of reconstructing every possible input file, right? So therefore, it's going to make an error in for some input sequences, but we want to make sure that the probability of that error happening is small, right? So the probability of error is basically the probability that xn hat is not equal to xn, right? And in this case, what is the probability of error going to be? So it is going to make an error if xn is equal to this or it is equal to this. Whenever the input is either 0, 0 or 0, 1, you are sure that the decoder is going to output the correct input file. But then if it is 1, 0 or 1, 1, the decoder is going to output 0, 0 or 0, 1, which is not equal to xn, right? So what is the probability of error?
50%, sir.
I'm sorry, can you please repeat?
Half, sir.
Yeah, it is going to be half. So it is the probability of 1, 0 plus the probability of 1, 1, which is half, right? So therefore, when we're talking about lossless compression, we can either study variable length compression with zero error or fixed length compression with some probability of error. Right? And in both cases, we have this notion of rate. So here it is k over n, k is fixed. Whereas for variable length compression, the average rate is expectation of k of xn divided by n. So the goal is to make the rate as small as possible. And if you want fixed length compression, then you want the probability of error to be as small as possible. Whereas in variable length compression, anyway, this xn hat always has to be equal to xn. So all we want is that the average rate is as small as possible. Okay. So this is lossless compression. Yes. Any questions?
Sir, the probability, I think it is a point.
I'm sorry, Shilomoni, I can't hear you.
The probability is 0.25, I guess, sir, because the last two ones, I think the last two codes, those probabilities are
Correct.
0.125, 0.125.
Correct. Sorry, my mistake. Thanks for pointing that out. So it is 0.25. So it is 0.125 plus 0.125, which is 0.25.
Yes.
Thanks for writing that. Right. Okay. So when we're talking about fixed length compression, we want the probability of error to be as small as possible, the rate to be as small as possible. For variable length compression, we want the average rate to be as small as possible. Now for lossy compression, again, we won't be talking about lossy compression in this particular course, but we allow xn hat to not be equal to xn, and therefore we want to make sure that xn hat is approximately equal to xn in some sense, and that is generally measured using some measure called a distortion measure. D between xn and xn hat, and the goal is to, again, you can either do fixed length compression or variable length compression. In this case, instead of demanding that the probability of error is small or that xn hat should be exactly equal to xn, all we are happy with is that on average, the distortion is less than some amount delta. So you specify some parameter, which is the maximum distortion you can, the distortion that you can tolerate, and then you design compressors with the same metrics such that the average distortion is less than some specified amount. Okay, so one example of a distortion measure is the mean squared distortion, which is on average what is xn hat minus xn squared. Right, so it is just expectation summation I equal to 1 to n of xi minus xi hat the whole square. So you want the mean squared error between the output and the input to be as small as possible. So this is the mean squared error distortion, and this is sometimes used. In the context of audio compression. Now, depending on the application at hand, you would choose a different distortion measure, but for a specified distortion measure, you can design a compressor for which you minimize the rate and at the same time also ensure that the distortion is less than this specified amount. Okay. So we'll stop at this point, but if there are any questions, I can take them now.
So this lossy compression is only applicable in case of like when we are sending on the net. But for the local case, it may not be applicable, isn't it, sir?
It depends, right? So even lossy compression, you may just want to say reduce the quality of an image, right? So there are plenty of converters where you can decrease the resolution of an image file. You can take a JPEG image, which is maybe 1 megabyte, and you can always convert it to 100 megabyte JPEG image by reducing the quality. And that's an example of lossy compression.
Right.
All right. So anything where you're okay with a certain loss of quality, that's an example of lossy compression. Any other questions? Okay, so if not, then we'll stop here. We meet tomorrow at 9 a.m.
Thank
Thank you.